Everything is made of atoms, and those atoms are composed of three subatomic particles: the proton, the electron, and the neutron. The proton and the neutron are both found in the nucleus and comprise the majority of the mass of an atom. The mass of an electron is significantly smaller and is often ignored in calculations, but it does have some. If you change the proton of an atom, what you will do is change the element. So changing lead into gold, for example, is only a change of 3 protons, which we could do with something like a supercollider. If you change the number of electrons in an atom, you are going to either make it a cation or an anion. A cation will lose electrons, become positively charged. The way I always remember that is the T was a plus sign. Or it will gain electrons, become an anion. As electrons are negatively charged, I increase the negative, it becomes a negative ion, An ion. If you change the neutrons, what you will do is make an isotope. That could be a radioactive isotope or just a regular isotope, but what you will be doing is changing the mass of the atom, because a neutron is not charged, but it does have mass. So protium has 1 proton and no neutrons. Deuterium has 1 neutron and 1 proton. Tritium has 2 neutrons and 1 proton. They are not ions, they are not different elements, they are isotopes. As we saw earlier, structure is equal to function, and so atomic structure determines the behavior of molecules and elements. And really, all of chemistry comes down to valence electrons. Atoms with incomplete valence shells tend to fill those shells by interacting with other atoms. These interactions of electrons among atoms may allow atoms to form chemical bonds, which are attractions that hold molecules together. So chemical reactions make and break chemical bonds to form molecules of different shapes. And if you change the shape in biology, you change the function. The first type of bond we're going to talk about are ionic bonds, which are formed by an electrostatic attraction after the complete transfer of an electron from a donor atom to an acceptor. The acceptor atom attracts the electron because it's much more electronegative than the donor atom. If you look at the example below, an atom such as chlorine that contains 7 electrons in its valence shell needs 1 more electron to have a full valence shell. If we use logic, it's going to be simpler for it to grab 1 more electron than it would be to give up 7. So with sodium having 1 in its valence shell, it wants to get rid of that electron. Chlorine wants it, so chlorine will take it. So under the right conditions, atoms like chlorine will steal an electron from a nearby atom like sodium. This ability to pull electrons away from other atoms is termed electronegativity. Atoms with a valence shell that is almost full are more likely to be electronegative because they have greater reasons to pull electrons towards them. Electronegative atoms are not negatively charged, but they are more likely to become negatively charged. Ionic bonds are very strong in crystals, but in biology they are considered very weak because they are fragile in water, and as we are living organisms and we are water-based, all of the chemistry in our bodies is aqueous chemistry, so the bond is relatively weak. The second major grouping of bonds are covalent bonds, which are shared electrons rather than transferred electrons. These are very strong in biology, strong overall, and they form what we typically think of as compounds. Now, different elements have different electronegativities, so in a covalent compound, the difference in electronegativity determines how equal the sharing of electrons will be. With something like a diatomic element, where the electronegativities are the same, it is going to be a nonpolar bond. The electrons will spend equal time near each nucleus. However, with something like water, it's going to be polar covalent because oxygen has a much higher electronegativity. Therefore, it has a much stronger hold on the electrons. So oxygen will become partially negative and hydrogen will become partially positive. This is important in biology because that partial positive charge on the hydrogen allows hydrogen bonds, which are extremely important. Outside of the regular bonding of ionic and covalent, there are some weak chemical bonds, or at least chemical associations, that are important to the chemistry of life. Hydrogen bonds, like I mentioned a moment ago, are very important. Hydrogen bonds provide many of the crucial life-sustaining properties of water, stabilize the structures of proteins and DNA, which is the building blocks of cells. When polar covalent bonds containing hydrogen are formed, the hydrogen atom in that bond has a slightly positive charge, which you can see in the diagram on the right. The hydrogens have a partial positive. Because the hydrogen is slightly positive, it's attracted to neighboring negative charges, and it forms a weak attraction. Individual hydrogen bonds are extremely weak, extremely easily broken. However, they occur in very, very large numbers in water and in organic polymers, and the additive force can be very strong. For example, hydrogen bonds are responsible for zipping together the DNA double helix, and if that was not true, life would not exist as we know it. Like hydrogen bonds, van der Waals interactions are weak interactions between molecules. It's the attractive and repulsive forces, the positive and the negative relationship. It can occur between any two or more molecules, and it depends on slight fluctuations of the electron densities, which leads to temporary dipoles, positive negatives, around a molecule. For these attractions to happen, the molecule needs to be very close to one another. It's only very small scale. They help form the three-dimensional structures of the proteins in our cells, so they're very important for life. Hydrophobic interactions are kind of along the same idea. It's the relationship between water and hydrophobes, which are low water soluble molecules. Hydrophobes are nonpolar molecules and usually have a long chain of carbons that do not interact with the water molecule. Like the mixing of fat and water is a good example. Hydrophobic interactions are important for the folding of proteins, which we'll see later on. They keep proteins alive and biologically active, decrease the surface area, and reduce the undesirable interactions with water. Hydrophobic molecules, like we said, tend to be nonpolar and prefer other neutral molecules and nonpolar solvents. Hydrophilic molecules, on the other hand, are molecules that are typically charge polarized. They're polar and are capable of hydrogen bonding, enabling it to dissolve more readily in water than in oil or other hydrophobic solvents. There are about 25 of the 92 naturally occurring elements that are essential to life. Now, that number is going to vary from species to species, but the big four is pretty much uniform amongst all living things: carbon, hydrogen, oxygen, and nitrogen. Together, these four molecules make up 96% of living matter. The other molecules, like calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium, make up most of the remaining 4% of an organism's weight. Um, there are also elements called trace elements that are required by organisms in extremely small quantities, such as chromium and copper and fluorine and tin and zinc. But overall, there are six that you need to remember, and that is shown as the mnemonic SHNOPS, CHNOPS. This mnemonic will come back several times, so make sure you learn it.